Okay, so let's talk about the problem of the day. And again, part of the thing in dynamic programming, I believe, is kind of one that if you see enough examples of what's going on, you hopefully develop a pattern, see kind of what the pattern of it is. And some of these problems look kind of weird when they're homework exercises because they're kind of false problems, not false problems, they're sort of toy problems. But I want us to try to understand them, this one anyway. Okay, so it says that we are given a problem that we have a string of n characters where there are marks. We know where we want to break this string into pieces. And we're going to, what we're allowed to do is to saw the string at any one of these points to create two strings, okay? And the cost of the sawing is the size of the string that it has. That's kind of what they are saying. So let's take a look at an example here. Here we have a string that is 20 characters long, right? It goes from 1 to 20, okay? There are saw marks on the thing after 3 characters. So maybe we put 3 here. Okay. What was the next one? 8. And what was the other one? 10. Does everybody kind of get that idea? And we want to saw this string, okay, to eventually break it into these 4 pieces. The cost of sawing something is the size of the pieces, is the length of the thing that we are working on, okay? So let's look at 2 different ways to saw this, just to make sure we understand what the problem is. And if you don't understand what the problem is, there's no way of solving it. Is that clear? So what if we saw it over here from left to right? What are we going to have after we saw it at size 3? We're going to have one string of length 3 and another string of length 17, right, where there is a saw mark now, 5 spots into it, and, well, let's keep the positions the same. Still at these kind of positions, at position 8 and 10, okay? How much did it cost to saw it there? Okay, the first sawing of the string, how much did that cost? 20. Now if I saw it over here, what will it cost with the next sawing? How much will that cost? 17. Does everybody see it? Because this piece is now of size 17. And then we've got that chunk. And I've got this other one piece, which is now how long? Is it 12? Yes, it's 12. Okay? And if I now saw it, how much will that cost? 12. And does everybody see at the end of this, I have got 4 pieces, right? And the cost of it was, what was that? 39. Does everybody agree? We could have also done it from left to right, right? Okay, that's from left to right. Wait, is it 49? Did I add it up wrong? Yes, I added it up wrong. 20 plus 17 is 37. 37 plus 12, this is 49. Does everybody agree? Good. Now, if I saw them from right to left, okay, what would be the cost of that? Okay? If I saw it from right to left, how much does the first cut cost? 20. And now I've got this string to work on. Does everybody see that? Now, what would be the next cut I make is this one that was at position 8. How much will that cut at position 8 cost me? How much? I didn't hear that. How much will it cost at the second cut? If I've cut it here, it's 10. Does everybody see that? And the next one is going to be what? Okay. The next one would be cutting it at the last spot. That piece was of size 8. I believe that piece is going to cost 8. Am I right? So doing it that way would cost us 38. Is there any other way to saw the strings? What would be another way we could have sawed the string? Somebody. Yes? We could have done 8. First, cut the thing at 8. How much if we had cut it in the middle at first? How much would that first one have cost? 20. Now how much would it cost to cut this one? 8. And how much would it cost to cut this one? 12. So this would come out to be 40, and that's no good. Does everybody see that? Okay, so the winner was 38. And the algorithm question is, if I give you a string like this, how do we find the cheapest sequence of cuts? Okay? Any ideas here? I want an algorithm for it. Any ideas how we would go about that? Yes?
You could do backtracking and try every scenario.
You could do backtracking, but if you do backtracking, it will take how long? Well, there's n choices for the first spot, right? If there's n possible cuts, you've got some tree of n by n. This looks bad, okay? So that's a bad thing, and I'm asking for n cubed. So that's not the way we look for get an n cubed guarantee. Yes?
So we're going to take the length of the string at this point plus the dynamic minimum of either removing the first one or the last one.
Okay, what you're saying here is you're saying I'm going to come up with a recurrence relation. That's what you're saying. Is that what you're saying?
Yeah.
Okay, so if we're going to do it by dynamic programming, you need to come up with a recurrence relation. And before I come up with a recurrence relation, I need to come up with what is my function that I'm trying to compute. So, what is give me a name, a number, what's the name of your function? You can call it whatever variable you want.
Get shortest.
Okay, that's too long to write. I usually use a single variable. What? Short, that's too, let's say call it S. That seems like a nice one. Okay? Now, S of, what are the arguments to S?
S, it's got the string right now and the array of cuts. Or the list of cuts somehow.
You're telling me that it's got the list of cuts, what's the cuts you've made so far stored?
No, the cuts left to make.
The cuts left to make. Okay? So, how do we describe the cuts left to make?
Lengths of string.
The positions of where the cuts are,
yeah.
Okay? Is there a way we can describe where the cuts are in a concise language, recurrence-like thingy?
Yeah, we can define the index of where we cut.
Okay? Does everybody see that when you didn't cut this thing, you get a sub-range of things? You can't have an arbitrary set of cuts in a wood. So that if there was an input set array of cuts, okay, the positions of the cuts that you have are described by where was the leftmost cut that you did make and the rightmost cut that you did make. The next one that you made. Does everybody kind of get that? So what is the way that I would be writing it? I think what you're saying is, let's let this position of the cuts array, the total cuts array, let's call it C. We could make that a global thing or something like that. But let's say that I've got L and R are my arguments. Okay? And I want my function to be what? What is the value of this function? We agreed it's called S, but what is it?
So if there's no more cuts between left and right, so
Okay, you're telling me how to compute it. Before I even get there, again, I can't think that far in advance. I want to think, what is this function that I'm trying to do? It's going to do, yeah?
So to find the left index and right index and find what is the unit time to figure out how to cut that.
Okay, what I say is, what is the minimum cost to completely cut the substring from C sub L to C sub R. Okay, let's think what this means. My original array looked like what? Maybe the left part of the string started at 0, then there was a cut at 3, there was a cut at 8, there was a cut at 10, and it ended at 20. Does everybody kind of believe that? I think that this is my C array of the positions of where the cuts are. How many people see where I got this array from? Any questions about that? Like, where did you get that array? I don't understand. Should I include 0 and 20? Now, this is a matter of finesse. I want to claim that if I include 0 to 20, then every subrange is described by a start and end here. Where if I don't include them, there's something funny about the beginning. Okay? So I happen to believe in including that. I think that that's better. Okay? Any questions? Okay? Now, what am I going to be asking? For any L and R, what is the cost of the complete cut from C of L to C of R? So if I gave you, in this case, what would S of 0, 5, C be? 0, 4. That's a 0, 4. What would the value of this be? Function B by this definition. Does anybody know? What? 4. It's not 4. What is it? Yeah? Okay, I want this to be equal to 38, if you understand my notation. Now, why is that? Remember, this was the description of the of the cuts. Does everybody agree? What are the indices of this array? If we assume that the indices are from 0, 1, 2, 3, 4, what is the whole problem that you want to know the answer to? I claim that the cost of cutting C from 0 to 4, positions 0 through 4, is the cost of cutting up this entire thing. Does everybody see that? Any questions about how many people see this? You got to have the language. Again, the first moving part here is how do you describe what you want to compute? Okay? And once we have what we want to know what we want to compute, then we can compute it. Okay? But if you don't know what you want to compute, it doesn't do it. Any questions about the formulation here? Okay? Okay? Any questions? What would, so do people understand what this function is? If you do, then what would the second step of dynamic programming be? Now that we have, yes? Well, find a recurrence. The base case is a perfectly respectable part of our recurrence. What is a base case? Give me a base case for this.
Left and right are equal.
So if you want to tell me what is S of I, C. Okay? That's really what you want to say. What would that be? Does everybody agree with that? That the cost of cutting up, if there's nothing in between the two cuts, it costs nothing. The strings of no length, right? Are there any other base cases we know? Yeah? You with the hat. What is S of I, I plus 1? That's a good one. What is that? Does everybody see that that is C of I plus 1 minus C of I? Isn't that right, what we would say on this language? That says that if we've got a piece here, okay, well, actually, let's just think about it. Is the cost of this thing going to be 3? That's the length of it, okay? Is that the cost of cutting it? Or if I just gave you a string, I guess we'd have to define. If I gave you a string with no cuts in it at all, what would the cost of it be? Okay? This is a definitional question in our problem, right? Okay, if the cost of cutting something that didn't need to be cut was 0, this would return 0. Does everybody see it? If the cost of cutting something that doesn't need to be cut is the length of it, okay, then it would be the length of it that we have here, right? Which do we think the problem is asking for? Okay. What should the answer of that? And I don't really know, but let's go to the definition. It says that to break a string into 2 pieces involves copying the string. Okay. Do we believe this cost us anything or not? Let's take a class vote. Okay. Does this cost us anything or not? Okay. Who here says that we should pay 0 for this? Who here says we should pay the length of the string? Seeing more 0, so let's make it 0. Okay? That's a possibility. Okay, fine. Now, if we want a recurrence, what is our recurrence relation for the general case? What is the cheapest way of doing it? Okay? Can anybody give me a recurrence relation for the general case? Or try. Anybody else? You.
So, if the function is SIJC,
S sub I, comma J, comma C.
it will be the minimum of SI, comma K, comma C,
Min of S of I, comma K,
comma C,
comma C,
plus S K, comma J, comma C, where K is in between I and J. And
Oh.
plus,
so K is equal to,
K is in,
K goes from I to J,
yeah, and plus the C of J minus C of I.
This looks very good to me. So let's think about this for a second, and let's make sure we see where this is coming from. Okay? What is this gentleman telling us? He is saying that the cheapest way to cut the stick from the ith position to the jth position, that cut is going to go someplace. Does everybody agree? There's going to be a first cut, whack, you're going to use to cut the string, right? What is the cost, whack, when you make that cut? That is the cost of, actually this is the minus, right? This here is the cost of the cut. Does everybody see that? It had a string that went from the jth position to the ith position. This was the cost of the cut, right? But after the whack, what did we have to still do? We had to finish covering up the string that was to the left of us, and the string that's to the left of the cut, and the string that's to the right of the cut. And how do we solve those? Those are over smaller subranges. Does everybody see that? So, what is it? This, in principle, has got to be smaller than this subrange. From I to K is a smaller span, should be than I to J. K to J is a smaller span than from I to J. If we've done these guys first and they're sitting in the table, we can just look those values up. Any questions about where this recurrence comes from? Okay. Any questions about this? How many people see understand the recurrence? How many people don't understand the recurrence and want to know? Want to? Okay. Any questions? Yes. A question like, can you explain that again, is another way of asking. Okay, so let's think what this is saying. If S sub ij is defined as the cheapest possible way to completely cut the substring from CL to CR, okay, what do we know about the cheapest way to cut these things? Well, it had to have a first cut in it. Does everybody agree with that? Once we've made that first cut, what is the cost of it? That's the cost of the length of this thing, right? That's the cost of Cj minus Ci. Does everybody agree that this is the length of the string that we're cutting? So regardless of where we put the cut, this is the penalty we're paying, right? Do you agree with that? But once we've done it, if I choose to cut it here, what's the cost? It's the length of the string, plus the cost of finishing the job there, plus the cost of finishing the job there. What is the cost of finishing the job here? Well, now I have to divide from the ith position cut to the kth cut if I chopped it here at k. Does everybody agree? And on this side, it's from the kth cut to the jth cut. Okay? So this is where the recurrence comes in. Any questions about that? There's one minor thing making me a little nervous here, but just to go through it, what's making me nervous? K goes from I to J. What is it that bothers me about that? Okay? It bothers me a little bit because it can get into an infinite loop. Does everybody, or an infinite recursion thing, right? When K is equal to I, what is this Kj going to be? Ij. Does everybody see that? And so that would be bad karma. It's not always getting smaller. How do I avoid that problem? Yeah? Right, so I want to say from I plus 1 to j minus 1 sounds good. We don't want the intermediate cut to really be at the end, right? Any questions about this recurrence relation? Okay? What I'm kind of hoping, where I think your head should be at this point, is, oh my God, I didn't see exactly how I specified this initial function. Okay? But once he explained to me how I specified what the definition was, yeah, I now see that this recurrence relation is the right thing. Okay? And I see that this recurrence relation can't be that complicated to find because one of the students in the class found it, right? Okay? That's good. I know, no complaints. Okay? Any questions about that? Yes? Why is S04C38? Well, we decided that 38 was the cheapest possible way to do this, right? When I went through all three possibilities for this example, did we agree that 38 was the cheapest? Do we agree that the arguments, if this is index 0, 1, 2, 3, 4, for this array C, then from 0 to 4 is exactly the problem I have on that there slide, right? So therefore, C of, where I have it, yes, C of 0, 4, S of 0, 4, C has to go to 38. Any questions about it? Okay. Any questions about this thing? Yes? Well, are there any intermediate dynamic programming problems? Well, what's good is there's going to be a homework assignment. You're going to get plenty of them. Okay, so I would say I recommend looking at, what do I recommend looking at? So I do agree that there's a lot of moving parts you have to see this. But none of the moving parts, once you see them, they become relatively straightforward. Hopefully some of the problems that are in the homework will be accessible. Hopefully I'm going to go do a couple more, another dynamic programming problem, edit distance, which is a very important and hopefully simpler recurrence. And maybe that will help it sink in. And we'll talk about more of these next class. Yes?
I think the minimum might be 37.
You tell me there's a way to do it at 37. How do you do it at 37?
With 10, then 3, then 8.
10, you want me to do, I see. You want me to do 10 as my first cut, and that would cost 20, right? And now once I cut it here, I've got this piece of size 10. You want me to cut where? 3. Now 3 is good. That would cost 10. And now you're absolutely right that this is in fact now a piece of size 7. The last cut should only cost me 7. Does everybody see that if I did that cut properly, this really should be 37? Any questions about it? Now, why is the right answer 37? Let's see if we can look at this and solve this thing mechanically and see if we could have come up with that 37. This may be getting a little dangerous. Let's fill in the table on this thing to see how we would do it. Okay? What is the table here? How many arguments are there? There are 2 arguments, and they go from what? 0, from basically if n is the number of cuts, both of these go according to n. Does everybody see that? Right? Let's fill in a table here. Try to decide what I want to erase. Is this stop here? Okay, now we're looking at a professional presentation. Okay, let's look at this. If this goes up here. Is that right? I don't know if this does it. Or is this am I going to get killed? Okay, good. Okay, what is this now going to be doing? Let's try to fill in a table here. Let's see if we could have gotten that 37 using the recurrence. Okay? What do we know? There's the first argument. It would go from 0, 1, 2, 3, 4. Does everybody see that? The second argument goes from potentially 0, 1, 2, 3, 4. Does everybody agree? What values here are 0? We know, let's say that this is the first one, L, and this is the one for R. Does everybody see that? What are the values we know from our incidence from our initialization? Yeah? We know that 0, 1 is equal to what? 0. We know that 1, 2 is equal to 0. Does everybody agree? We know that 2, 3 is equal to 0. And we know that 3, 4 is equal to 0. Does everybody agree? Right? Now, do we know any other things? Right now, how many spots still don't we know? I claim there are 6 spots we don't know, right? Does everybody agree with that? What is the cost of cutting? This goes from 0 to 2. What is the cost of cutting from 0 to 2? Okay. What's it going to be? 8, right? There's no decision. There's only one cut point in there, right? Does everybody agree that that's 8? What is the cost of cutting from 1 to 3? What is the cost of that going to be? How much? I didn't hear that. Does everybody see that this is equal to 7? How many people don't see that? Okay, does everybody, okay, why is that? Because if we looked at it, again, if I rip this out, it will collapse it. But look, it's laser pointer, right? That's what we do here. Okay, what is this thing saying up here? This is saying that if we have, from I to J, if we had a situation, the situation from 1 to 3, what does it look like? We've got 1 is defined by point 3. There's a cut at 8. And there's a cut at, the boundary is defined as 10. Right? What's the cost of this one cut that we make? There's no decision about which cut we have to make. It's got to be the middle one, right? And what's the cost of that going to be? The length of the string. And what's the length of the string? 10 minus 3. Does everybody agree? Okay, now we're in business. What is the cost of going from 2 to 4? What's the cost of going from 2 to 4? That's what this box is. 12. Does everybody agree with that? Good. Now let's fill in some of the other cells, at least one more. What is the cost of going from 0 to 3? Right? That would be the case of the image that would, to be honest, that looks like 0, 3, 8, and 10. Does everybody agree with that? What is the cost of this going to be? But 10 is the end of it, right? I guess this is the right end. What is the cost of this going to be? The total cost is going to be 10 plus, and we've got two different parts, right? If we made the cut here, what would the cost be? Well, to finish this would have cost 0. What would this have cost, going from position 1 to position 3? We have it. That's 7, right? Does everybody see that if we make this cut here, the cost is going to be 10 plus 7? And what if we didn't? What if we made the cut here? It would be 10 plus the cost of going from 0 to 1, right? From 0 to 2. What is 0 to 2? That would be 8. Which is the cheaper of those two? 17. Does everybody see that? So this is 17. Do you see how this is being made to work? Do you want me to keep going on this? Or who here says keep going? Who here says stop? Okay, I'm hearing mostly stops. Oh, it's a close call. Okay? But do you kind of see what you do now? I'm just evaluating this recurrence. And what's cool is I know the items here are waiting for me. So I can fill in what's the cheapest way to go from 2 to 20. And once I know what that is, now I have the way to figure out for all of these what that value would be. And this one we've decided is 37, right? Any questions? Okay? Yes?
So when you set the recurrence relation that IIC equals 0, does that mean that we would have to flip the diagonals well with zeros?
So this says that we could might as well fill in the diagonals with zeros, right? That's a perfectly harmless thing to do. And if somebody's really going to ask you that, then it's good to have it in there. But notice we didn't need that to solve more interesting problems, right? You know, I would say that it's probably good housekeeping to fill it, but it's not really, in general, if you're going to say, don't ask me any stupid questions, okay, then you wouldn't need that one, because 0, 0, is 0, right? But if not, we can put it in there. If we know it, we might as well put it in there. Any questions? Any questions about how this worked? There's one more detail here. What is the running time of this algorithm? Right? Here's a dynamic programming algorithm. What is the running time of that algorithm? How would we figure it out? Okay? To me, it's the number of boxes times the maximum cost per box to fill in. Right? If we have n cuts, so the size of our thing is of n, how many boxes are there to fill in? Okay, how many wants to make a proposal? How many boxes are there in my table that have to get filled in? Yeah? Half of n by n, which, since I think in big O world, I think of it as n by n. I've got an n by n table here, right? How much time does it take to fill in? That's n squared boxes times how much does it cost to take to fill in a box? What is the most expensive box to fill in? Okay, well, if we look at our recurrence relation, the thing that's governing the cost of the box is that min thing. Does everybody see that? What's the maximum amount of time that min loop can spin around? When you go from 0 to n, right? If so, that min loop spins around n times. And what's it doing every time it spins? Look something up in the table, plus look something up in the table, plus look something in the table, look something in the table, subtract and add, right? It's a constant effort every time that loop spins around, right? So it costs n time per box. Therefore, it's n squared times n, which means it's an order n cubed algorithm. Any questions about that? Okay, how many people feel they understand this now, where this came from, anything like that? Any questions about that example? Yes?
I think you can do this in linear time with the greedy algorithm.
You tell me you can do it with a greedy algorithm, and I see no reason. Okay, if anything you want to do with it, you can do anything you want with a greedy algorithm under two conditions. One is you're willing to accept it be wrong, or you have a proof that it is correct. You need a proof that you're telling me a greedy algorithm is what? What would the greediness be? The logical greediness might be make the middlemost cut. That's the one you want to do, right? Whack it in the middle, okay? And you need a proof that that's right, okay? Now, it's clear that that is not right in terms of the middle of the cuts, okay? Because if so, then you would probably want to make that middle cut here first. Does everybody see that? The middle cut in this example would have been 8, okay? So it's certainly not true, because since that did not lead to the optimal solution, cutting it in half. So it's certainly not true that making the middle cut is right. You may say making it geometrically in the middle. Maybe that's a great thing to put on the exam, okay? Find me a counterexample or a proof to that, okay? Let me think about that. That might be something to think about. Yeah?
The thing is not the greedy algorithm is not cut in the middle. It's like we have like maybe n breakpoints. We will end up with n plus 1 pieces. And we look at the first pieces and the last pieces. We compare which one is greater, and we cut that piece as the first time. So the first one will cut as the n, cut as the 10 pieces. Now the last pieces is 10, and the first pieces is 3. In second time, is the first pieces is 3, and the last one is 2. So we cut the first one, so that leads to the 37 answer.
Wait, are you giving me a counterexample or are you giving me a proof? Okay, I don't think your proof is right, okay? But you have plenty of time to work on it before the exam, okay? Maybe, okay? Think about it, okay? Any questions? Again, if you have a careful enough proof that you might be right, but I'm pretty sure you're not right, actually. Okay? Any questions about it? I know this is right. Why do I know? Because the first cut's got to be somewhere, right? The first cut can either be here, here, or here. And which cut am I taking? The one that minimizes the total cost. So did that cut minimize total cost? Well, by definition, it minimized total cost. Okay? So mine has a proof. Yours either does or does not. Think about it some more. And if somebody has a proof or a counterexample, let's talk about it next class. Any questions? Or on the midterm. Any questions? Okay, good. Okay, what I would like to do now, because it's been quite delayed, is to get to the idea of edit distance. Okay? So edit distance is a very important, probably the single most, let's say, commonly seen dynamic programming application by undergraduates who take this course in some level. It's an important problem. You can see that it's an important problem. This thing with the string, chopping the strings, may not strike you as important. Okay? Edit distance is related to inexact string matching. Okay? It's related to misspellings. One word in that sentence, my first sentence is misspelled. Which word is misspelled? Anybody see? Which word is misspelled? Misspell, okay? Misspell is misspelled, okay? I think it's got 2 S's, okay? Now, what would you like to know? What is, you probably have used a spell checker, right? And that spell checker will often say, you type in Skiena, okay? You're writing something, you type in Skiena, it's going to tell you that's misspelled, right? What does it tell you the right word to helpfully replace it? We'll probably say something like skiing, or something that is 1 letter change from it, right? Is everybody kind of used to that? So what we would like to be able to do is for 2 strings give a sense as to how far are they apart in spelling space, okay? And the cost metric that we use for edit distance is that the distance measure between 2 strings is the minimum number of changes that have to be made to convert one to another, right? How do you convert Skiena into skiing? Let's think about that. Skiena is S-K-I-E-N-A. How would you convert that into skiing? S-K-I. How do you spell skiing? Another I-N-G, 2 I's? Okay. How would we convert Skiena into skiing? What do we have to do? Okay. To my sense, what I've got to do is this part looks okay, right? But I probably want to substitute the E and replace it with an I, right? I'm happy to keep the, the ends the same, okay? And I want to convert the A's to the G's. Does everybody agree that I could do it with 2 substitutions is the distance between Skiena and skiing? And what would it be if we misspelled skiing the way I was tempted to do, where skiing is S-K-I-S-K-I-N-G? Let's say I had only 1 I. What would be the cost of editing it? I would probably say match, 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 drop the E entirely, and then do a substitution at the end. Does everybody see that? It's still 2 changes. Only one of them is now a delete instead of a substitute. Any questions? Okay. So what edit distance is doing is it is trying to express the distance between words by the, using 3 different types of changes. If I want to convert a string S to a string T, one way I can do it is by a character change. So shot can become spot by changing that H to a T. Does everybody see that? We could also do an insertion. I could insert a new letter into the first pattern, okay, to make it match the other thing. So if I want to make a go into a gog, one way I could do it is to insert into the first string a G. Does everybody see that? And what if I want to make a change to pattern S to make it hour, to make it match hour? What change would I make to hour, the time, to hour, the possessive? What do I need to do? Yeah? You could say I could insert the H into T or delete the H from S. Does everybody see that? So insert and delete are sort of similar cases, right? But the way that but they're different because of what string we're doing them to. So in this connection, we're saying we're going to make all the changes to S to get it to equal to T. And we might either decide to add in a letter to S or decide to delete an letter from S. Any questions? Okay. Any questions? So the edit distance is given to strings. Find the minimum number of changes you need to convert one string to another. Now, can somebody give me a more expensive way to convert Skiena into skiing? One possibility is delete, 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 delete. Insert, 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 insert. Okay? So it's not that it's hard. Oh my God, how can you possibly convert into one string to another? That's not a hard thing. The hard thing is how can I cunningly figure out what are the minimum number of changes I need to make in order to do that conversion. Any questions? Okay. So we're going to learn this through the magic of recursion. And let me show you this, because this is going to lead to a very, very simple recurrence. First, we need to have written in English, what is our function? Let's let dij be the minimum number of characters, changes to convert the first I characters of string S into the first j characters of string T. Okay? What am I going to claim? If I am converting two strings into each other, if I have a string S and I have a string T, if I am going to convert S into T, I'm going to have to do something at the end of this string. Does everybody kind of see it? What are my possible things I could do at the end of the string? I could take the last character from each string and see whether they're the same. Does everybody agree with them? If they're different, I could decide to match, that I have to substitute one to another, right? If they are the same, I could say, look, it's a match. I don't have to pay for that. Does everybody see that? What other things might I decide to do at the end of this thing? I might decide to insert a character at the end of S. Does everybody see that? In which case, the only reason I would want to do that is to match the last character of T. Does everybody agree with that? Right? Or I might want to delete the last character from S. Right? Anything else I could do at the right side of these strings? I claim not. Any questions about that? Which one of these is the best operation? The one that's going to give me the minimum number of changes total in the string. Well, which one of them is it? The answer is I can't tell. But I can tell if I know what the cost is of editing the prefixes of these strings into each other, and the prefixes of these strings into each other, and the prefixes of these strings into each other. Because the cost, if we match this, is going to be 0 plus the cost of matching that into that. Or, if it's an insert, 1 plus the cost of matching this into this. Or 1 plus the cost of matching this into this. So what is the recurrence relation? The cost of editing the first I characters of S into the first j characters of T is the minimum of the I minus 1 S j minus 1 if the characters are the same, because I don't pay for doing the match of the end of these things, right? Or one more than the cost of editing the prefix to the prefix if the characters are different. Or if I decide to do an insertion at the end of S, then I am going to be, that insertion that I'm doing is supposed to match the last character of T, right? So once I've taken care of that, the cost of this is 1 for doing the insertion and the cost of editing the first I characters of S into the first j minus 1 characters of T. Or I could be deleting it from the first character from S, in which case what's left of the I minus 1 characters. And I've got to edit those I minus 1 characters into the j characters of T, and I pay for the operation. This is the recurrence, because I'm going to minimize I'm going to pick the operation that minimizes the total cost of the job. There is a cost of the last operation, 0, 1, 1, 1. The total cost of the job is the cost of what is left after I've done the job, okay? And the cost of what else you paid in the course of the process. Any question? Again, I just thought of a bad analogy. Suppose you pay a hitman $100 to murder somebody. Maybe your algorithms teacher. What is the cost of the total job? Is it $100? It's $100 plus whatever time you spend in jail for ordering the hit on the professor, right? Did you get caught or anything like that, right? There is a cost for the actual act, and there is a cost of the implication of the act. Does everybody kind of get that idea? That's the point I'm hoping to make there with that. Okay? Any questions about this recurrence relation? Does everybody see what this is saying is this is the min of bracket this or this or this or this. Okay? How many people understand the recurrence relation? Any questions? Anybody not understand the recurrence relation? Any questions about it? Like say it again is a fine question. Yeah? Could I say it again? Okay? My claim is that this is a recursive algorithm because why? Edit distance takes two strings and returns the cost of transforming it. If I shorten the strings, okay, okay, I end up getting an edit distance on a smaller problem. Does everybody see that? What is the cost of editing the strings together? Well, in whatever the best possible editing is, there's something going to be done with the right. Which is the best move? To shoot the professor or not shoot the professor? The question is, ultimately, what is the total cost of the last operation? Did you pay? You saved $100 by not hiring the hitman, right? Plus the cost of the rest of the job, okay? Does everybody see that? And these are smaller string edit problems. If they are smaller string edit problems, that's why we're solving it recursively. So the cost of editing the full I characters into the full J characters can be expressed by the cost of the operation plus the cost of the rest of the strings. And each of these has different recursive cases, depending upon how many characters you hack off of each string. Okay? Any questions about it? Any questions at all? Okay? Yes? Where is the base case of it? You're 100. That's always a good question. Okay? What is a base case? A base case is something you know the answer to. Is there any case that somebody knows the answer to? Yeah?
It might be D of 0, 0.
D of 0, 0. How much does it cost to edit the first 0 characters into the first 0 characters? How much time does that take? How much does that cost? 0. So D of 0, 0 is 0. Okay, now we have a base case. Any questions? Yes? Well, now the question, let's think of other cases. What would D of 0, 1 be? Does everybody agree that it's 1? Right? Because you're entering one string into an empty string. Okay? Actually, more generally, I guess what you're telling me is that D of I, comma 0 is equal to I. Is that right? Okay? So that seems like a pretty big, right? To edit I characters into the empty string, you got to delete, 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 right? What is D of 0, comma I? Does everybody agree that's also equal to I, right? So these are pretty powerful base cases. Okay? Any questions about that? Now it might be that you could have figured out D of 1, 0 was equal to 1 by calling this recurrence. Right? Let's think about it. If we call D of 0, 1, what is D of 0 minus 1 is going to be what? That's going to be d of minus 1, 0, right? That seems like a bad thing, right? So maybe what we would want to say is, again, I think that's an argument for specifying the full basis cases. Yeah?
But when we do that, that's if s of sub of I equals to t of sub of j.
You know,
Actually not there because it's 0.
okay, I like these base cases the way that you have them. This is the base cases that I would like. Another base case that might have worked is d of 0, 0, and saying d of anything negative. Negative, you know, anything where one of the arguments is negative. Maybe that was infinite, so you didn't want to choose it at all. Okay, but I think I like this. This is the one that I would use. Okay, any questions? Okay, any questions about what the recurrence is? Now, because I'm running a little behind, let's just think what I want to do. Here is, just for your entertainment, a recursive implementation of this recurrence. Does everybody see that string compare is calling string compare, string compare, string compare, right? This is a recursive call, like your recursive Fibonacci program, right? And what is this going to do? It's basically saying that the cost of editing S to T is, there's three possibilities. I end on a match, an insert, or a delete. The cost of it, I have the arguments being adjusted here, I minus 1, j minus 1, I, j minus 1, j minus 1. Here I pay the cost of, is this character the same as that character? I pay 0. If not, I pay 1. Here I pay 1. Here I pay 1. This is the dynamic, this is that recurrence implemented as a recursive program. What is the time complexity of this program? Turns out to be exponential. Why? Because it's a recursive program the same way the Fibonacci program was. Does everybody see that? It's not storing anything, so it's recomputing it. Okay? If, on the other hand, we have our table where we store for every possible I and j what the cost of, okay, editing the first I characters into the first j characters is. Although there's an exponential number of potential calls that would be made if we did this without storing anything. There's only n squared possible pairs. If n times m pairs, or a string of length n times a string of length m. So my state here is going to be quadratic instead of exponential. Any questions? So I am going to represent this by an array of length n by m. That's my dynamic programming table. And in each cell of my matrix, I'm going to maintain what's the cost of editing the first I characters into the first j characters. Okay? The other thing I'm keeping track of here, though, is the parent. Okay? What does the parent mean? If you think about it, if we go back to our recurrence here, the minimum cost for editing from the first I characters to the j characters is doing something for a last operation. It's either doing a substitute or an insert or a delete. Does everybody see that? And that means that the value of this cell is going to depend upon either this cell as its parent, this cell as its parent, or that cell as its parent. So I'm saying keep track of where you came from. That's going to be useful to actually reconstruct where the changes were. Any questions? Okay. This is the recursive program. A dynamic this is not a dynamic, this is a dynamic program for implementing edit distance. Let's go through the code a little bit just to make sure. What am I saying? String compare the first S to T. I'm going to say find the longest amount of the array. I need to initialize my dynamic programming table. What are my basis cases? We said that they were the row and the column initialization. If I have my matrix M here, the cost of editing, 1, 2, 3, 4, 5, 6, 7. Does everybody agree that I have to initialize my first row and column? And that's what is happening up here. Then what am I doing? For I goes from 1 to the length of the string, for j goes to 1 to the end of the string. What am I doing? I am walking down the array like this, filling in the value of the recurrence as I do it. What is that value of the recurrence? If you can read it, it's saying at position ij, I can do one of three things. I can end on a match, in which case I would go to element ij, I minus 1, j minus 1, look up what that cost, and then pay the cost of the match. Or I could end on an insert, or I could end on a delete. Does everybody see that? What are the cells in the matrix that end on an insert for a delete? If we are looking at this position in the matrix, this says what's the cost of editing the string that let's say the string, the first character. Let's say this is ABBA, and this was Okay, what's the cost of editing the A into an A? Okay, actually this should be starting here to be precise with my my indices. Okay, what's the cost of editing an A into an A? Well, you say it's 0. I can't say that. I can say it is the minimum of 3 possibilities. Since A equals A, I could do it in a cost of editing 0 to 0, which was 0, plus the match cost of A, which would be 0. Or I could have paid 1 more than the cost of doing this insert, okay, which would be 2. Or I could have paid 1 more than the cost of doing that deletion, which would be 2, which is the minimum of 0, 2, and 2. 0, that sounds like a great way to do it, right? So this gets a value of 0, and that diagonal was its parent. More than that, notice that in this table here, if this is cell I comma j, where are the other cells that I'm going to be looking up? I minus 1, j minus 1 is over here. Does everybody see that? This is what? This is I, j minus 1. Right? Does everybody see that? And this is I minus 1, j. So what is interesting? How do I fill up this array? Basically, I'm going to be, for every cell, looking at my 3 neighbors to it. And I'm going to pay either 0 or 1 plus this value, depending upon whether this character here matched that character there. Or I am going to pay 1 more than this, or 1 more than that. And I pick the minimum of the 3. Does everybody see that? So that's what I'm doing now. This fancy code here is pretty dumb looking, but it's really just taking the minimum of these 3 things. Does everybody see that? And the minimum cost of those 3 is what the cost of cell ij should be. And so I keep the cost. What is the ij cost? And what is the parent? Which direction did I come from? Did I come from there, or there, or there? Any questions about that? Okay, any questions? Okay, what is important to see here? I can tell the tensions are winding down. Okay, what is important to see here? And if you don't see it, you're in trouble. Okay, and you need to figure it out. First, you need to see that this is a recurrence relation that will find the minimum cost, edit distance cost, of any string to any other string. Does everybody get that idea? Okay? Second, you need to see that if I have this recurrence relation, what's the cost of it going to be? What's the time complexity? Well, this goes from 0 to the number of characters in S. This goes from 0 to the number of characters in T. If that's n and m, that means there's n times m boxes. Does everybody agree? How much time does it take to fill in a box according to this recurrence? Okay, how much time does it take to fill in the box according to this recurrence? Yeah? It should take constant time if the spots are filled, right? Look this thing up in the table. Test if the character is the same. Look this thing up in the character. Do an addition. Test if the character is the same. Look it up and add 1. Look it up and add 1. Does everybody see that? Take the minimum of 1, 2, 3, potentially 4 things if we wrote it in a clumsy way. Okay? This is a constant time to fill a box, and there are n squared boxes. Any questions about it? What? N times m boxes. And it took how much time constant per box? The total time is n times m times 1, or order n times m. Any questions about it? Okay? So what's important to me? From an algorithm theory point of view, exam-like thing, it's important to be able to understand where a recurrence comes from like this, why it's right, okay? What its time complexity is. From a point of view of, can I actually program this thing? You should understand where the code is and where the table is. In fact, on the next homework, I let you implement one of these and find what the edit distance is between 2 strings. It's important to look in the bookkeeping and see how you get the bookkeeping is a real thing. It's not like, it's really just basically filling in this matrix, okay? Any questions? Okay? And that's the important thing to understand about this. What order could we fill in these matrix cells? Let's think about it, though. If I had this as my initialization conditions, and in fact, every cell that I need are the ones that are just above me, that way, and diagonally, right? Could I fill in the cells going along a row first? If I fill in the cells like that, do I have the cells that I need waiting for me? How many people say yes? How many people say no? Well, the answer is yes. Why do I know that? When I fill this thing in, do I have the guy above me? That was my initialization. Do I have that guy? Yes. Do I have this guy? Yes. Right? Does everybody see that? So I could fill these guys in like that if I wanted. Does everybody agree? Could I fill them in going down a column? Is that something I could do? Yes, I've got that guy there, I've got that guy there, and that guy there. Am I right? Could I fill them in along diagonals? Let's try to fill them in along diagonals. Could I fill them in like this? Would that be legal? Yes, because the 3 guys I need are there, right? Could I fill them in from right to left? Could I fill them in like this? No. What do you mean, no problem? I have it. I don't got it. Right? Does everybody see that? So long as I have an evaluation order, which is governed by the way, these two loops. Okay? I fill the elements in, and they are there waiting for me. Okay? Any questions about that? Yes?
So it would be a possible, would it be considered just optimization then to pick a different strategy based on having different RJ values to fill out your matrix?
So we may be saying, which is better? To fill it in by rows, to fill it in by columns, or to fill it in diagonal? Which is better in terms of a running time strategy? They are all exactly the same. Every box still gets filled in, right? And it still takes constant time. Okay? Is there any possible advantage now? Now I'm going to ask you a subtle question. Is there any reason why one of those orders might be better than the other? Okay, yeah?
Maybe if you're working multi-threaded, that different threads solving applications.
Okay, so maybe you could imagine some parallel thing going on. Okay? That's an interesting idea. Which way would give me the most parallelism if I wanted to work on it? Would it be better off going along a row, or a column, or along a diagonal? Well, a row does me no good because all of them require the guy before them done. Does everybody see this? I'm doomed to doing it sequentially along a row. Does everybody see that? I'm doomed to doing it sequentially along a column. But what about these diagonal fronts? Does everybody see that? These guys are ready for me, right? These guys are simultaneously ready for me, right? If I really wanted to do this in a multi-threaded way, then maybe it did make a difference. In this class, do I want to do things in a multi-threaded way? No, okay? But you see where that gives you the freedom. So understanding what's going on enough gives you the power to think about that. Any questions? Any questions about this? Okay, how much time do I have? Let me tell you one advantage that you could possibly have that's more real in here. What happens if we wanted to reduce the amount of memory we needed? Ultimately, we're interested in the cost of getting to the last cell, right? This is going to tell me the cost of editing the full string here into the full string there. What if my strings are long enough, I don't have the space to keep this whole matrix? How much of the matrix do I have to keep? Okay, I'm seeing faces. What is this? Okay, yeah.
Perhaps just the last row column.
Does everybody see that if I just keep the last row and